Very good morning, guys. So today we are going to discuss the case study on Tacoma Narrows bridge type aircraft Flutter. It is happened with the tailed aeroplane. So let us take some tails like V-tail aeroplane is there, T-tail aeroplane is there. So how this Tacoma Narrows bridge similarity is happening in the aircraft due to this Flutter. That will have a case study discussion on several technical discussion. Let's begin.
Yes. Talking about the narrow bridge collapse, first we had to understand about Flutters. Flutters dangerous, self-inflicted aeroelastic instability happens in the aircraft. And the aerodynamic forces, elastic instability, and inertia impacts, which leads them to grow oscillations instead of damping them. The flutter will leads to some collapse. The best example was the Tacoma Narrows bridge collapse in 1940, which happened as well. And the unique flutter is unique in it fits itself when once triggered, the energy flows amplifies the oscillations. A similar mechanism occurs in aircraft, especially in the tailplanes. Due to their thin flexible structure, their exposure to turbulent flow leads them to this collapse.
Understood that flutters occur due to the instability which is created by the airflow once it has the main wing, and this lightweight structure tail section is having some elastic limits, and due to this initial disturbance it start oscillating or vibrating. That oscillation vibrating leads to this flutter. That is what we understood this discussion. And next, what technical discussion?
I want to tell you about why the tail part is more vulnerable to the flutter. So first of all, its position. It is in the wake part of our aircraft. So wake is nothing but where the flow will come after interacting with the main wing. So at the interaction of the main wing, the flow will be a laminar. But after the interaction, it will be more turbulent and have some frequency. So if you take the tail part, it is most made up of very light material. Like for our example, so if we take a solid material, like if I just slap it here, it will just not vibrate, just be in the same position. But very thin material, if you take, I just made a contact, so there will be some wobble effect. So that will create the frequency. So we have a two frequency here. So what will happen is, if the frequency and the frequency of the tailplane matches, there will get a flutter effect. So this is the reason why the tail part is more often getting flutter. So also it is located at the farmost part of the CG. So many movements, also bending movement also acts, it will increase the aeroelastic effect. So this is why the tail part is more vulnerable to the flutter effects.
Based on this discussion, comparing with other parts, tail is more disturbed due to this flutter. So one is the turbulence, and the other one is it is more away from the CG. It means that tail is due to counteracting the moment which is created during takeoff and landing. That is what we are keeping the tail. Without tail, we will have unstable aircraft. Anyhow, we need a tail, but only thing is we need to reduce the vibration frequencies. We know the structural frequency and the operating frequency. We should not match these two frequencies. Once these two frequencies get matched, the resonance will take place. This resonance is, we are all if it is interacting with inertia force, elastic force, and aerodynamic force, then this will cause the flutter. Yes.
So, hi everyone. I'm going to tell about the overview of this case study. So in this case study, engineers have observed an unusual vibration in the horizontal tailplane of a regional jet prototype during the high-speed flight testing. This issue appeared during the testing close to Mach 0.5. Initially, the vibration was mild and undetectable. So, but the aircraft crosses certain speed, the oscillation became unstable. So it was larger and faster and more synchronized. Flight data indicated that the vibration frequency was approaching one of the natural vibration of the tailplane, crossing signature of the flutter onset. So this gave engineers about finding a hint of the similar vibration, similar to the Tacoma Narrows tailplane, and this was happening.
Okay, one example is how this match the Tacoma Narrows field similarity how it is happening. The 0.7 Mach they have tested. That means 0.7 Mach means it is the incompressor flow. In compressor it will be 7 and 8 touches the transonic flow and it leads to compressibility effect. Like shocks will get involved. Without getting compressible effect, before compressible effect, it is happened due to the only the Mach values, the fluid flow creating the dynamic instability because of this flow disturbance. That is similar case as happened in the Tacoma Narrows. That is what this experience happened in the tail section.
Next, I'm Srinita. Next, we are going to see about aeroelastic movement. Actually, what happened in Tacoma Narrows bridge type fluttering tailplane when torsional or oscillation planes in the and tailplane started twisting slightly due to aerodynamic loading and vortex shedding from the wing wake. Just like vortex hitting the Tacoma bridge, asymmetric vortex from the wing struck the tailplane at a certain frequency. And frequency lock-in at high speed, vortex shedding frequency matches the tailplane torsional natural frequency. So positive energy feedback loop, instead of damping out, the airflow pumped the energy into the motion, causing it to grow. Thus the process flow is a small oscillation that causes resonance, which results in the rapid twisting motion, and it causes dangerous structural failure.
Coming to the technical understanding, here the natural frequencies involved and the structural moments are involved. These two things were different frequencies, and due to the wake effect or the vortex shedding will have some natural frequency and it will striking the tail section, and this gets locking the control surface movements, and these movements will not, it should act as a damping. Anyway, that means it should be suppress the energy. What are the energy that's transformed from the main wing vortex shedding, it should get suppressed, whereas it is positively increasing the oscillation and producing more amplification, which leads to resonance, and this will cause the flutter.
I was going to share the investigation and diagnosis. After the incident, engineers conducted aeroelastic investigation, and from that they find the tailplane's torsional stiffness was slightly lower than predicted stimulations, and the computer models estimated the turbulence in the wing wake. The manufacturing changes have reduced power wing thickness and the flutter margin, and the safe wing buffer was smaller than required Mach number. And then we have the engineering fixes like corrective actions. Then we have reinforced the spot to increase the torsional stiffness, and updated CFD and FEA models for better turbulence predictions, and added mass balancing weights, shifting the natural frequency away from the vortex shedding frequency, and revised the flight testing envelope to avoid risky speed zones until fixes were implemented. These changes eliminated the flutter risk and restored structure integrity and safety.
Yes, coming to the suppression of this flutter, it's technically explained by adding some imbalanced masses so that the natural frequency will shifting from the shedding frequency, and structural modification can be added by the spar dimensions, and the studying this component using CFD, how it is responding to the various fluid flows in computational analysis, FEM analysis. This will help us to reduce the noise frequency and the system frequency, that will reduce the oscillation and resonance, which will reduce the flutter time. Also, we can reduce this flutter by understanding the position of tail wing can be away from the references axis of the fuselage, so that most of the fuselage tails will be not in the fuselage axis, it will be in upper higher order, the position will be in high in the tail section. That is because of the upwash effect and downwash effect. Once the airfoil is entering to the aerofoil or wing, it will act as upwash, and what is leaving to the main wing, it will act as downwash. This downwash will act as a vertex shedding. That frequency will not hitting the tail point and in tail section. That is what, after the several aerodynamics and structural properties and CFD, all the experimental testing, they made the position of the tail wing should be high from the main wing position. Then this is how they have reduced the aircraft. So this research is still, they are testing several conditions, and they are not entirely there, it is not stopped, it is happening in some cases, and this research and this discussion helps to increase the safety aspect of the component, and which is taking the reduction and controlling the flutter in the aircraft. So these are what we have discussed today. That's a great discussion. You understood that what is flutter and what is vibration, how this flow is interacting, and what is how aerodynamics, how important is aerodynamics is. Huge bridges as well as the aircraft, and also the elastic properties of the materials, and natural frequency and system frequency. These things are really well done. That is so great understanding. Thank you.
Thank you.